So I think is that what you meant? Sure. No, no, of course. So that's one of them. Derivatives rules for exponents. Integrals rules for exponents. Daphne? E to the x divided by x plus e.
E raised to 4x plus c.
Any other things? I think rules about logs, sines, cosines. How do I use them? And is there anything else that kind of fits into this finite math part? And I don't mean just this, by the way. I really just mean this as an example of things. I think about limits as being another topic.
Trigonometry.
Sure, the fits into the finite. Remembering, structuring, prioritizing. I mean, those are the things that I'm really trying to get you to do, rather than me tell you what the outline should be. When you start to think about these things and prioritize them, you've got more comfort in understanding what the entire field is, rather than just seeing me do it and then kind of quickly forget it. So what is the problem that you fear most in finite math? And I'm going to stick in some other things that I think fit here. Solving equations belongs to finite. Right, like example, e to the x is equal to 3, what's x? That requires I do some things about solving equations. Other kinds of things that could help. I'm thinking you've forgotten entirely about the finite math part. I really am a little concerned. Things like, I think just very general ideas, things like, what does it take for something to be a function? So what does it take for something to be a function? I just have to be able to write f of x, right? I've got to have this idea that whenever I supply a value of x, there's a unique outcome for this, right? I mean, I'm saying this and you're smiling, but my guess is you might be smiling and not really like get what it means. And what about one-to-one functions? That it's a function first. So each x gives me a unique y, each y gives me is associated with a unique x. And why do I care about functions being one-to-one? It's got an inverse. So when we approach a problem like this, because I know that e to the x is a one-to-one function, I can use the inverse function of this natural log in order to solve this kind of an equation. Sine of x. Is it a function? Is it a one-to-one function? It has an inverse. So,
It's stipulated on a range that it covers.
so, I mean, I've got to think about things like, if my sine of x is doing this, now does each value of sine x, is it associated with a unique value of x? No. And that really has some implications when you think about solving equations and coming up with results that for you to get an answer to this, I've got to come up with a range restriction that says I'm only going to look over 0 to, actually, 0 to 2 pi. And if I go beyond that, then I start to get multiple values of x that could generate this particular value of y. Those are kind of important to do because, I mean, keep in mind that we're doing things like looking for fixed points. Those fixed points involve solving equations. So important characteristics of functions, I think, are fair game for this. I'm going to go to, I know how to make it. Even without it. Polynomials, one-to-one functions. Ooh, that's the first question that I'm going to ask. Are polynomials one-to-one functions?
Derivative cubic functions can be, but they can also
You don't have to go to cubic, but just look at a quadratic. Y equals x squared, not one-to-one. Number systems. What reasonable number systems have we got? Well, integers is a nice system for us. Do we do anything that involves rational numbers? Not really. I mean, I know that real numbers are made up of rational numbers and irrational numbers. It's okay for me to really, we haven't done anything to make a distinction. And complex. What else from finite could be important for you? We put in solving equations. Factor against an example. We use inverse functions. That's another part of it. So let's think about the problems that you agonize the most over from the finite part. So when I think about word problems, boy, you know, I've got to probably come up with some kind of a strategy for dealing with them. These, you know, I mean, I do need to understand the concepts of these things. But for the most part, these things, other than maybe this idea about solving equations, and maybe a little bit of stuff about the rules for these other things operating, they're not about doing things, they're just about understanding what the results mean and how they fit into, probably fit into word problems. So, word problems. How to think about them. Anything you'd add to this? Judith? Why is including units useful? Mostly because it just gives you a really quick check about whether some kind of an equation I've written out makes sense or not. And I know that maybe this is like so basic that you're bored, but my guess is you're still gonna have problems with word problems. I think another thing that could be useful is, what's an answer look like? And one of the things that I'm going to suggest here is structuring problems. Can help a little bit with this. Have we got some ideas about how to come up with some equations? Sometimes these things are driven by, I'm going to call it a process. I think about mass balance. Maybe some other ideas about how to think about coming up with these equations. To a large extent, the equations that you come up here within finite are not terribly different from the process that you would use if you were trying to put together a differential equation. They're not really that different. So some good examples that we've done about some equations. Reminder, I think maybe the problem with balloons. So we have a person standing, another person standing, and they saw a hot air balloon. And then now, based on knowing how far apart these people are, and knowing what the angle is, trying to determine how far away and how high the balloon is. Picture probably is a really useful way to think about doing this. Another problem that you could think of that we've done that involves some planning and defining variables. So let's call this H, let's call this D. Some other problems that involve the street light problem. Yeah, everybody hates the street light problem. but trust me, it will save your life someday because you will not walk directly under the street light when you're crossing the street. I care about you guys. Another problem that really fits into this finite word problem. I think another problem that we've done is the radioactive decay. So this was, I don't remember what that thing was, I think this was thorium. And when it decays into some other thing, which will then start to decay. I'm gonna give you a hint, what I just described here is an SIR model. The only thing that's different is, instead of having thorium, you have healthy people. These are people that are infected, but they eventually recover. Exactly the same kind of model. Every atom has to go somewhere, and it goes either stays here, or it goes here, or it decays into something else. Any other models that you can think of that work? Oh, we had the car that was leaving Chicago and somebody else was leaving Bloomington, and I wanted to know where they met. Easy, hard. Well, I mean, I think one of the things it's designed to do is to tell you something about being careful about definitions. If people are on different clocks, you could have like the clock of where one person is, a different clock where the other person is. You know, you don't even know what the clock is about where they meet. It just means that you have to sort of think about sort of segmentation and possibilities. I'm going to give you like one more thing that should usually help you with these word problems, and that's to start simple. You have to fight your urge to just like write down the answer. Oh, I know what the answer to this is. So start simple, meaning don't look at the entire problem. Use segmentation. Look at part of the problem, understand the part of the problem, and then put the pieces together. And maybe this problem would be a good example of that. I think even maybe this problem would be a good example of that. If I know something about what this distance is and this angle, I can describe something in terms of the height. Know something about this distance and the angle, I can say something about the height. Well, the height is the same for both of them. The distance is different, and that's the reason why the angles are going to be different. Where? That word? Segmentation. So look at part of the problem. Yeah, just look at parts of the problem. Anything else that fits into this word problem thing? So I think about the next chunk of stuff as being differential calculus. Things that fit into this are limits, derivatives. Anything else you want to add to the list? There's two more. You can give me like either one of them. I'm not going to put that into this part. Then there's three more if you want to put it into this part. One of them I would call differentials. And I think the fourth one would be partial derivatives. So limits, why are limits useful? How should I think about them? What is it required for me to go limit of f of x as x approaches a equals? What do I need in order for that to happen? The answer is not. When I plug a into f of x, I get L. That's not a requirement.
What function approaches the same number on both sides?
So that's one of the things that I'm going to require, that the limit of, as x approaches a from the positive side of this is equal to the limit as x approaches a from the negative side of this. If the right-hand limit is equal to the left-hand limit. Anything else? That the function be defined at a, right? No, don't write that down yet, especially if you're using ink. That's what you want it to be, and the world would be great if that's what it was. But what would be the prototypical problem? Now, by prototypical, I mean the one that you just look at and you go, this really captures this process about right-hand limits, left-hand limits, and a limited existence. So if I take a look at a function like f of x is equal to 3 plus 2x, what's the limit? Of f of x as x approaches a. So, how did you get there? You plugged in a for x, right? So what I really want to do, I want to think about this in the sense that as I get closer and closer to a, like I'm just a little bit less than a. What happens to this when I'm just a little bit less than a for this function? I get 3 plus 2 times a number that's a little bit less than a. And as I get closer to a, from the negative side, this is going to get closer to that value that I would get if I plug that in. And if I've got an approaching this from the positive side, then as I get closer and closer to this, from the positive side, I'm going to get 3 plus 2 times the number that's just a little bit larger than a. That's the way I should think about limits. Not just, oh, I can plug in the value and then be done with it. You really should give this a little bit of thought. Let's take a look at another function. The limit of this function, this actually should be under the limit being not under the function. Let me suggest to you that a lot of what we do when you're thinking about looking for stability in systems, finding fixed points, trying to figure out what a system of equations is going to do near a fixed point, we're really doing stuff that involves limits. I want to look at what happens when I get really, really close. If I start at a place that's really, really close, where does it tend to go? Does it tend to go to this point? Or does it tend to get repulsed away somehow or deflected away? So this would be a good question to ask on the exam, because it's gonna like stump everybody.
Is it infinity? Because like as you go from either direction, you make numbers smaller and smaller, and one divided by a smaller and smaller number is getting closer and closer to infinity.
So I'm gonna have I do notice that if x is positive or x is negative, as I get close to it, I get the same result on both sides. In other words, I'm gonna get a small negative number squared, that's positive, or a small positive number squared, that's positive. So no matter how close I get, this left-hand limit, right-hand limit things, this requirement is gonna get satisfied. And now the question is, well, what's this limit? And as I'm getting closer and closer, this tends. So does that mean that this limit exists as positive infinity? Well, we talked about that delta epsilon definition of what it meant for a limit. This doesn't satisfy that delta epsilon definition for a limit. Meaning that if I'm in a little box for our function, let's think what this function looks like. This is going to be going like to infinity and infinity as we get closer and closer to 0. But if we try to put together a little box around this, stuff is going to get outside of that box. So the answer is, I can tell what this function is, how it's going to behave, but it does not satisfy the formal definition of a limit because of that characteristic.
Can you just go to the delta epsilon thing then? Like,
Yeah,
can you write it out or something?
yeah. So we did this in class. So what this delta epsilon definition says is, if I think about being in a particular neighborhood for the result, like I'm going to describe a little area for the outcome, can I come up with a value for the x variable that's within some epsilon of the place that I want for this a? And the answer is, when I think about this box that I want to put around this, and no matter how small my box is, I should be able to do this, I can't come up with a range of values for the x's where this is always inside the box. I think that's the easiest way to think about the delta epsilon definition. Now let's compare this to something else. Like another very common thing to have happen is a function where I've got something like x plus 2 divided by x times x plus 2 divided by x plus 2. And as I get closer and closer to a point like 2, sorry, minus 2, the denominator becomes 0, and now I've got a problem with the definition of this function. So not defined at this point. But I noticed that if I want to come up with a box that I'm going to put around it, my delta, I can find a range of x's where the value of that function is always inside of it, inside of that delta. Here's my delta. Here's the range of x's, where the function, if it's defined, is always inside that range.
Where does the epsilon
Okay? So I just have to realize that this doesn't satisfy. So when people talk about something going to infinity, or going to negative infinity, that doesn't satisfy the definition of limit formally. But it's still instructive to know that it goes to infinity or not. What if I take a look at something like 1 over x by itself? What's the limit as this goes to 0? I notice that on the positive side, it's going to go to positive infinity. On the negative side, it's going to go to negative infinity. There's going to be a lot of functions that have characteristics like this, or really have instances where this function tends to just get bigger and bigger. A lot of our solutions to differential equations do funny things at particular points. Limits. So why do I care about limits? One of the reasons is because it's a fundamental definition for a lot of the things that we look at. I think about limits as telling me something about convergence. What happens is the time goes to infinity. What happens as the number of terms that I look at gets larger and larger for the n plus 1th term. Understanding something about limits is fairly important for a lot of things, and in particular, our definition of derivative depends on it. So I use the symbol dy dx. This is an operator equals the limit as delta goes to 0 of f of x plus delta minus f of x over delta. And I should think about delta. Remember, we should think about delta as being both this positive value and negative value. Because in my limits, I want to make sure that the right-hand limit and the left-hand limit are the same thing. So I should think about this as representing something like very close to what we've defined as sort of our way to get the limit for the derivative at a particular point. Let's call this point x0. I've got a function. I should go kind of plus a delta minus a delta. And I'm going to think about the chord between those two things as being a good way to numerically evaluate a derivative. Your tendency is think only positive, and I get it. You're upbeat people. I'm a pessimist, so I think almost always about only subtracting or dealing with negative values of delta. Between the two of us, we should get it, right? Positive and negative. Other ideas, partial derivative? I have a different operator in mind for this. My operator here is, I'm going to use the partial sign rather than a d. It really should be sort of technically correct when you do this. If I put d, y, d something, and that y is a function of more than one thing, it's not clear what exactly I'm trying to describe. The partial derivative, and when we talk about differentials in a second, we'll see. dy, partial y, partial t. So if I have a function that's a function of more than one variable, that means that I should be taking the limit as delta t goes to 0 of f of x and t plus delta t minus f of x and t divided by delta t. So in other words, partial derivative, difficult to do? Absolutely not, but it's an important concept more that you understand what it means. I should treat the variable x in this like it's a constant, like it's just some symbol beta, and don't do anything about that. And then just do the derivative like it's a function of one variable, t. Differentials. What if y is a function of two variables? then one way to take a look at this differential is a question about, well, how does y change? What are the things that are responsible for y changing? The answer to this would be that I should take the partial of y with respect to x times the amount of change that I have in x, plus the partial of y with respect to t times the change in t. That's called a total differential. It's allowing my function to be described by something where x is changing and and t is changing in order to tell me about the change in y. When you build regression equations with more than one variable, you're essentially trying to describe something about total differentials. When I think about a multivariate Taylor series, I'm thinking about something that's really motivated by something with a total differential. Now, this total differential could be like in two variables. Or my differential could be in one variable, dy equals the derivative of y with respect to x times dx. And I think about that as kind of being a motivator for a first order Taylor series approximation. It starts off with a differential by saying, how does y change? It changes because x changes. Or how does y change? It's because x changes or t changes or what are the other variables are that are part of this. So I think about these as being sort of the motivators for Taylor series, and then I've got Taylor series. And I have Maclaurin series. Why do I use one or the other? You can stand up. Remember the balloon problem? If you stand up and look, you're more likely to be able to see further. Get a chair and stand up on it. Nobody's gonna. I'll try to.